We have reached the edge of the solar system. We have photographed Pluto. We have landed on a comet. But no mission in the history of spaceflight has ever pointed straight up or straight down toward the poles of the sun. Not one. Look closely at every mission line ever drawn in the solar system. Apollo, Voyager, Pioneer, New Horizons, Cassini. Every one of them moves in the same flat direction, sideways. And the reason has nothing to do with funding, nothing to do with political will. It has to do with a force so fundamental to how our solar system works that escaping it may be physically impossible with any rocket we can build today, or possibly ever. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity. As it fell inward, it began to spin. As it spun, it flattened, like clay on a potter's wheel. The sun formed at the center. The planets formed in the disk. That disk is called the Ecliptic. And every planet, every moon, every asteroid, every comet orbits within it. Earth moves through this disk at 107,000 kilometers per hour. Every spacecraft ever launched inherits that speed automatically, swept along by a current 4.5 billion years old. Flying sideways, out toward Mars, Jupiter, Pluto, is comparatively simple. We are already moving in that direction. Flying up is something else entirely. Going up, perpendicular to the disk, straight towards the sun's pole, requires cancelling all 107,000 kilometers per hour first, then rebuilding that speed in a completely new direction. The physics does not allow shortcuts. No engine ever built carries enough fuel to fight that current and win. Here is what almost no one knows. The man who first mapped the geometry of this problem did it in 1609. Johannes Kepler, court mathematician to Holy Roman Emperor Rudolf II, spent years calculating why the planets move in ellipses, not circles. His third law of planetary motion is the reason we understand orbital speed today. And it is the same law that tells us, 4 centuries later, why going above the sun is almost physically impossible. Kepler never knew he was drawing a cage. In 1990, NASA and the European Space Agency launched a spacecraft called Ulysses, the first mission ever designed specifically to study the sun's poles. Physicist Edward Smith and his team at the Jet Propulsion Laboratory knew the truth immediately. No rocket on Earth could launch Ulysses directly upward. It would require 3 times more fuel than reaching Pluto. Instead, they sent Ulysses on a 5-year detour to Jupiter. Let the gas giant's massive gravity grab the spacecraft and hurl it sideways into a new trajectory. The maneuver worked. Ulysses reached an inclination of 80.2 degrees from the ecliptic. 80 degrees, not 90. Even with Jupiter's gravity, the largest planet in the solar system, Ulysses still couldn't reach the true pole. The last 9.8 degrees were physically out of reach. They remain out of reach to this day. To understand why those final degrees matter so much, consider the numbers. Reaching Mars from Earth requires a velocity change of roughly 6 kilometers per second. Reaching Jupiter, around 9. But to fly a spacecraft into a true 90-degree polar orbit around the Sun would require a velocity change of over 24 kilometers per second. More than twice the energy needed to reach Jupiter. More than enough to leave the solar system entirely in the other direction. The most expensive destination in our solar system is not Pluto. It is not interstellar space. It is 90 degrees straight up. And here is what Ulysses found when it got as close as physics allowed. Above the poles of the Sun, the magnetic field opens up. Along the equator, the Sun's magnetic field is twisted, tangled, chaotic, pulled in different directions by different latitudes, spinning at different speeds. But above the poles, the field lines stretch outward in long, clean streams. These are called polar coronal holes. And the solar wind that flows out from them is faster, cleaner, and more powerful than anything measured anywhere else on the Sun. The solar wind above the poles travels at 750 kilometers per second. At the equator, around 400, nearly double. We had no idea until Ulysses crossed that invisible threshold. Carl Sagan spent his career arguing that our instinct for exploration defines us as a species. In 1990, he convinced NASA to turn Voyager 1's camera backward toward Earth, one last time, before the spacecraft crossed out of the solar system entirely. The result, Earth as a fraction of a pixel, suspended in a sunbeam. Voyager 1 is now more than 23 billion kilometers from Earth, the furthest human-made object ever built. And it is still moving within a few degrees of the ecliptic plane. Even at that distance, even after 47 years, every probe, every trajectory, every calculation contained within the same thin band. The disk holds everything. When Copernicus proved in 1543 that the Earth moves around the Sun, not the other way, humanity lost its place at the center of the universe. It was the first great demotion. What we are only now beginning to understand is the second one. We are not just small, we are trapped in a plane, and the space directly above and below that disk, the two largest and cleanest regions of our entire solar system, remains completely unreached and, in many ways, completely unknown. Right now, the European Space Agency's solar orbiter is climbing, guided by ESA physicist Louise Hara through a series of Venus flybys toward the steepest inclination any active mission will ever reach. 24 degrees, the highest humanity will reach above the solar plane within this decade. And from that vantage point, the true pole of the Sun will still be 66 degrees away, more than twice as far as everything already traveled to get there. Scientists will gather data and build models, but the pole itself will remain, as it always has, just out of reach. The most unexplored region in our solar system is not at its edge. It is 90 degrees above the star at its center. A direction no human instrument has ever reached, a region that exists in the one geometry our solar system's physics almost perfectly forbids. We have mapped craters on asteroids 500 million kilometers away. We have photographed the surface of Pluto. We have detected the gravitational ripples of black holes merging a billion light years from Earth. But the pole of our own Sun, the point directly above the star we orbit, that we have studied for all of recorded human history, remains to this day unreached. Not because we haven't tried, because the solar system built a wall we still don't know how to climb. Even now, after everything humanity has achieved in space, the Sun's true poles remain almost completely beyond our physical reach. Every direction in space is open to us, except one.